Hello everyone, and welcome to this session called Designing Applications in the Era of Many-Core Computing. If it was some other kind of session you were intended to go to, you can leave now. If you've seen me presenting last year the patterns for parallel programming, most of the session from last year would be in this one. So if you think that it will not bring a lot of value for you, you might find another session. Otherwise, I think we'll have a next 60 to 75 minutes of fun trying to see exactly how and what do I mean with designing applications for the era of many-core computing. My name is Tiberiu, aka TB Kovac. I am originally from Romania, but for the past 15 years I was living in Sweden. I was working with computers since the beginning of 1991, which makes it over 20 years of experience in that area. I worked with languages from Pascal, C, C++, Java, assembler. So I did my fair share of programming within almost any known programming language, actually. I started to train .NET since 2004 by becoming a Microsoft certified trainer. And I do a lot of work closely with Microsoft. I was involved with the multi-core research group at Royal Institute of Technology in Sweden. I am an INETA speaker and country lead for Sweden. I'm a Telerik MVP insider. And if you want to find me on Twitter, my handle is Tibor19, and you can use the hashtag MSTechhead if you think that's something it's worth tweeting about to your tweets. So, before we get started, let's look at the current state. A lot of work was done for the past 60, 70 years in the area of, in this research area of computing mainly, and for the past 50 years in the area of parallel computing. And some conclusion, or we came to some conclusion. And if you look actually at what happens right now in the academic area, you will get more or less the same kind of papers that will be submitted, and they will try to send exactly the same signal to everyone. So the first signal they are sending is that the clock speed has reached an upper limit and you can't increase that. And because of that, we still have Moore's law, and Moore's law said that every second year we'll get a double amount of transistors, which for a long period of time just translated it double the frequency, double the speed, of course, double the quantity of data that can be stored, and so on and so on and so on. So everything was doubling every second year. And the Moore law, as it states here, it's still alive and kicking, meaning that we still have exactly the same kind of power. We double the number of transistors every second year. But we can't do faster processors. So the reason, or what the hardware manufacturers start to do, they started to do multi-core. And if you look at the processors today, you already have like 8 cores plus hyper-threading that would look like a 16 processors or processing unit in your machine. You have machines with 12 cores actually, and hyper-threading that will look like 24 processors. So they are doing a lot of work in this area, and they are still providing a lot of processors or a lot of processing unit, and they are doubling the number of transistors every second year. If we extrapolate that, within 10 years from now, we'll have like 500 processors, or around that number. So you never know how long they will go with that. But it looks that they could still run on the same wave for the next 5 to 10 years, on the Moore's law wave. But there is a problem. The software for the multi-core, actually, it's hard. And it was demonstrated 40 years ago by a guy called Amdahl. And he said that every single time when you try to parallelize an application, you will actually have a problem because of the sequential part of your application, meaning that if you have a big enough sequential part, no matter how many processors you will add to your machines or for your applications, you will still get so much parallelization or improvement of your performance. So it will not be like it was until now. Every second year, we get a double amount of speed because the processors were double as fast as 2 years ago. And what will be the result of that? Angry bosses. They would really don't like us to not do anything and actually deliver performance improvements. So now we have to take those things seriously. So Normally, when you look at all those academic papers, they enumerate 3 reasons why multi-core programming is hard. Let's do that. First, it's hard to test. It's non-deterministic. You don't know exactly what happens because stuff might run in that machine or on that processor or on that processor or whatever. The coming of cloud computing actually will add even more uncertainty to this one, because you might actually ask for more processing units. You might get them on the same machine. You might get them on another machine. It's nothing that you might control. So there are a lot of factors that will affect the way we will do programming. So we need to make sure that we do it the right way. So conclusions of all those stuff and all those academic paper is that we and no one else has any idea how to solve this kind of problem, but the future is shiny and glorious. So we might still go to our bosses and say, you know what, we need to figure out how, but we will work on that and we will deliver more speed to your applications. Hopefully, at the end of this discussion, you will get at least an idea of how to do that. I won't give you the silver bullet for that, and I won't expect you to go from here and just press a button and say, now my application is parallel. I got some people doing that, and they had some problems, and I might explain them later on. So for today, I put up an agenda that we can see actually what we will go through. I will have some definitions, so we do understand exactly, or at least we will talk about the same thing. We will know exactly that we are on the same page. Then I will look at how to create some parallel applications. Then I will show how you can find concurrency in your application and how can you exploit those, which strategies you might use to exploit this concurrency. We will look at some algorithm structures and how can you structure your application to do that. We will talk about some supporting structures for that. And then last but not least, we'll talk about sharing state, because I feel that this is the root of all evil in parallel applications. If we know how to, or if we understand how the data is shared, we might have a chance in delivering better applications for our bosses, or for whoever is actually the one ordering the work. And then at the end, I will show some resources that you might find useful and that you might continue your journey into this space of many-core era. How many of you know the difference between multi-core and many-core? Okay, so not so many people. It's very few people. The difference it's quite thin. Normally, you call something that is multi-core if you have under 8 processing units of the same kind. If you have above 8 processing units of the same kind, or if you have 8 different kind of processing unit, like the processor in the PlayStation 3, for instance, then you will call it many-core, because there are different cores or different specialized processing unit. So that's more or less the difference. Is just a thin line between those two. It's not that big a difference. So let's start with the definitions. I will tell what is a pattern in my view and why I consider what I consider a pattern. Then I will talk about some pattern languages, and then I will show you the programming roles. And at the end of that, I will show you a demo application that I try to put up for this presentation, so that we can get a better understanding of what happens and how you can apply all those stuff in your applications. So a pattern is nothing else than a generally accepted solution to a recurring problem. So you had a problem, or someone else had a problem, and they tried to figure out what's the best way to solve the problem, and they came up with some kind of solution that might be interesting to show. So the solution or the patterns in my presentation will all be marked with this little sign, this little rectangle here, just to show that this is a pattern and draw some attention. Normally, when you talk about the pattern, there is a pattern that describes a pattern. So what does it mean? It means that you have some characteristics. When you get a pattern, you get a name for it, so you know how to call it, and you might actually discuss with other people. For instance, oh, this is a singleton, what we are using here. Oh, this is an MVC, or this is an MVVM, or whatever we might find suitable to talk about. Then we have a problem. What problem do we try to address with this kind of pattern? A context. When can you apply this kind of pattern? We have some forces that are actually influencing our solution to the problem. You have the solution itself. The solution, once again, it's not a silver bullet, so don't expect that this one will work actually and it will just solve your problem, whatever the problem might be. But it's a start for a solution. You will have invariants, stuff that are not changing and shouldn't change in your application when you're doing that. You have some samples. How can you apply that in practice? You have some known usages for this kind of stuff, and you have another related patterns that you might apply together with this respective pattern. So as I said, there is a pattern to describe a pattern. So by following that and by looking for those elements, you will know exactly what it is all about. Several patterns could be actually. Oh, wrong button. Several patterns could be actually combined to create something called a pattern language. And those patterns normally flow one into the other while you are trying to solve the problem at hand. You are trying to apply the first pattern, and then you'll say, okay, this pattern now it's actually a very good continuation on that. I can continue with that. I can continue with that. And that will create actually, several patterns will create this kind of pattern language. Do you know any pattern language? Design patterns is the most known one. The Gang of Four wrote it 17 years ago, and that's a pattern language actually. You would look at their patterns, they categorize those, they explain how to use them, they used all those characteristics that we are talking about just so we can have a pattern language. And when you talk about programming, we have something called programming roles. Let's just see, my computer just shut down. Hopefully we'll get back that one. Yes? So the first programming role that you will see is an application programmer. What's an application programmer? At least in my world, an application programmer, it's someone that it's very good at a specific problem. It's not a computer scientist. It's, I don't know, let's say an image, someone that will take some images and will do stuff with the images, or someone that is very good at a specific mathematical solution. But they are not good with computer programming. They know how to use a language, they know how to use some algorithms, they know how to use some stuff that are built into the language. Then we have a framework developer. The framework developer is that guy that will try to help the application programmer and create some of the algorithms that will be used actually by the application programmer. Then you will have a parallel programming framework developer. Normally a person that worked long enough with application frameworks, and then at the end he just started to create, or went into more into details, and then tried to parallelize all those kind of algorithms that are at hand. And last but not least, you have a platform programmer, persons that know exactly how any platform works or different platform works, and they can use the hardware, they can use the information about the caching when you do different kind of stuff on the specific platform or on the specific application. Normally, those kind of guys are like 1% of the programmers out there, if there are so many. And normally they work in companies like Microsoft to create those platforms or those frameworks for us so that we can use them in our applications. So I said that I will present a problem, and I have a question for you. Who's that guy? Do you know who that guy is? Swedish Chef, yeah, that's right. So, why the Swedish Chef? Because I was thinking about presenting a recipe. So, I was looking on the internet actually and tried to find some recipe that it's hard enough to do, you know, in a short time, and that has a lot of hidden parallels that you could actually use in your use to parallelize. So let's take a look at this recipe called the yummy goulash. You have some ingredients. The ingredients are like 400 grams of meat and 12 potatoes, some paprika pulver, some 2 peppers, some water, and some onions. That's what you need in order for you to do that. And then the instructions are quite simple. You got 4 steps. Peel and dice the onions, fry the onions, and then sprinkle some paprika, add some water, dice the meat, add spices, and so on and so on and so on. I know time. It's like 5 o'clock now, and everybody is hungry. I hope by the end of this you'll be even more hungry. But it will start a community party right under us, so would be just in time for that. So let's see how do I did that actually in my application. So what I did actually, I took a simple C# program, and I said, make goulash. That's the recipe, and I do step 1, 2, 3, and 4. Very, very simple. So my first step is to peel and dice the onions, then fry them, and then sprinkle some paprika, add the water. Second step would be dice the meat, add some spices, cut and clean the chilies. First cooking step, and then I will get the third step and the fourth step and so on. So everything that was in the recipe I am actually modeling in my application. Every single method eventually will call another method here that it's called do work. And do work simulates that it does some work for a certain amount of seconds. So in that case, I will say do cut the peppers or it takes like 120 seconds to do all the peppers. If you look at for instance, how much it takes to do dicing the meat will take some 20 seconds per gram of meat that you will get in your application, and so on and so on and so on. So let's run the application just to see what happens. I'm doing some calibration, some stuff just to make sure that 1 second it's it's the counterpart or whatever timing I have on that machine. And at the end, I can show an approximate number of minutes. So it takes like almost 200 minutes to do that. That's more than almost 3.5 hours to do a pot for 4 persons. And if you have kids like mine, they will actually go crazy after the first hour. So you need to find a solution for that. You need to find some way to improve that. And because we are several people at home, I mean, it's my wife, and I could have some child labor, put my kids to work and help in the kitchen with the stuff, then why not? I will try to see how it will be possible. Another thing I want to show you is that I'm using a machine, this small box here. It's actually an 8-core machine that I'm using as a demo machine, just to show what happens when I'm running the recipe. So let's do that again, and I will show this now. And we can see that the normal load on my machine is like 12% all the time. No matter what I'm doing, all my calculations are some spinnings around, so I'm just doing some divisions, so I put the processor at work. I'm not doing thread sleep or something else, because I really want to load my processor while I'm doing stuff like that. And then at the end, I will get 197, 199 this time, whatever. I mean, I will not get the same amount of time every single time. It's like real life cooking, Today it takes longer, tomorrow will take shorter, and so on. So the main point here is that my CPU usage was always 12%. That's 1/8 of what I have available in my machine. And a big family, big people at home, I can put them all to work. So let's see how to do that and how to make these things work in my advantage. So to create a parallel application, first of all, you need to look at the original problem. You need to analyze the problem, and then you try to find a concurrency. When you did find a concurrency, you will end up with some tasks. You will end up with some shared data by all the tasks and some local data for any of the tasks that you are running. Then you try to reorganize the data, and you will end up with some units of executions. You will have some new shared data structures, because it might make sense to find those and extract them from your applications. And you will end up with some extracted dependencies as well from between your tasks. And then you will use some supporting structures and implementation mechanisms, and the result would be some code that you will implement in your application. For the sake of this demo, and because this is a Microsoft conference, I choose to use C#, but you could use C++, you could use Java, you could use whatever language do you want, because everything from here is actually it's just patterns, so it's not specific to C#. Once again, I'm using C# because that's the language that I speak best. So let's start with finding concurrency, and we will start from the original problem, and we will end up with some tasks and some shared data and some local data. When you talk about that, there are two different pattern spaces or pattern categories, and one pattern. One pattern category called decomposition analysis, another one called dependency analysis, and the third one called design evaluation. So the first one, when you do decomposition, you can do decomposition in 2 ways. only those two. You can either do decomposition by data or by task. Of course, you can do some combination of those, but that's beside the point. So what you do actually, you either look at the task, what your application does, or you look at the data. What are you doing with the data? How can you parallelize that? Then you do a dependency analysis. You will need to group the tasks. You'll need to group the tasks in such a way that you will actually better use your resources. Maybe it makes sense to run specific tasks on specific processing units or in specific machines if you have several machines, or whatever you find necessary, or even you have some kind of dependencies, and then you need to make sure that you order the tasks and you still solve the same problem. Would be unfortunate to start to fry the onion before I peel it and dice it, or I start to dice the onion before I peel it, because the recipe would not be the same, the taste would not be the same, even though at the end I will end up with everything in a big cooking jar or whatever. And then data sharing. You need to make sure that you understand how the data is shared between those tasks that you have identified in your application. Because having this information and knowing this information will actually help you understand the problem better. And then design evaluation. Of course, you need to always ask yourself, is this decomposition fine enough or good enough so that I can continue with that, or I might find something else. I might even go deeper in that and find another one. So it's an iterative work like all the development we are doing. So we might find that it's good enough for the first iteration, but in the second iteration we might find something more. So let's start and see exactly what do I mean, or how do you do that in a specific problem. So if you remember, we had 4 steps. And those 4 steps actually were something like peel and dice the onions, fry the onion, blah, 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 blah. We did that one step after the other, one step after the other. Then the end result was that we got our recipe. We start to analyze the dependency between different kind of steps that we have here. The first one, peel and dice onions, actually creates a dependency. You cannot start frying the onions before you do the peeling and dicing. You need first to fry the onion before you add the paprika, or you need to add the paprika before you add the water. So this kind of dependency you still need to keep in your application. Then you have the next step, dicing the meat. Dicing the meat has nothing to do with any of the other steps. So I can actually remove that dependency from my application. So I'll remove that dependency. Then the next one, dicing the meat and adding spice or cutting and cleaning the chilies are not actually depending on this adding the water stuff. The only thing they are dependent on, or the only dependency they create, is that I cannot start cooking before I have all those previous steps done. So I will remove this dependency as well. Then peeling and dicing the potatoes is not dependent on the first cooking, but the next cooking will be actually dependent on the first cooking and peeling and dicing the potatoes. Same goes for cut the peppers and the last cooking step. So let's rearrange that a little. So just we follow exactly the same constraints and we try to solve exactly the same problem, because that's what we are doing actually. And the result would be something like that. We do first all those steps in parallel, or at least we will try to do that. That will need that we have enough horsepowers in our machine, or I will have enough hands in my kitchen, for instance, to help me with all those kind of stuff. Then I will have the next dependency, and then the next dependency. So the end result will be the same. And now I have a better look at how different tasks are created in my application, how they are dependent on each other. Is that okay? Okay? So let's look at the next step. Now we found some of the concurrency in our application. I haven't looked at the data yet, but we will look in a minute as well at the data and see exactly how the data is could be parallelized when we work with the data. So we have some algorithm structure, and the end result would be some units of executions and some new and shared data and some extracted dependencies from our application. So when we talk about strategies for exploiting concurrency, we have 3 different strategies. One strategy is called agenda parallelism, the second one is called result parallelism, and the third one is called specialist parallelism. So let's look at some of those strategies. The first one, agenda parallelism, when you take an algorithm and you naturally express that at some actions. So I have step 1, step 2, step 3. Or if we go a little bit fine-tuning, we will see fry the onion, peel and dice, and stuff like that. Those are my tasks in my application. So by doing that, I could look at them and I could find different kind of parallelisms that I could exploit. One of them is called task parallelism. And task parallelism, actually, it has two different kind of phases. One is called delightfully parallel. And delightfully parallel means embarrassingly parallel. It means that I have two tasks that are completely independent of each other. Then we have separable dependencies. I could find tasks that are dependent on each other, but I could take out those dependencies, and by taking them out, I will have actually another smaller, maybe delightfully parallel problem with some dependency that I need to run sequential, or that I need to run after all those parallel stuff are done at the end. Then we have a divide and conquer. Divide and conquer goes after the principle that you will take a big problem, you will split it into smaller problems that could be solved independently. And I will show both of them in code, actually. So let's move to this machine again, and let's try to see how can we change our code in such a way that we get some more parallelism. So let's start with this. I made a small method called make goulash parallel. It's quite self-explanatory what it does. So let me change that. So I will call this method. If I run the application right now, I wouldn't get any difference. It would be exactly the same thing as we did before, because everything it's actually the same methods called one after the other. Now let's try to parallelize this. I will use task class for that. How many of you have seen task parallel library? Okay, so most of you. That's perfect. How many of you have used lambda expressions and are familiar with lambda expression? That's perfect. Okay. So, then I will start with the first one. I will say something like task, and I will use the name like peel and dice onions equals, and there is a task class, and the task class has a factory static property. The factory static property has some methods, and one of them is called start new. And the start new method, it takes an action. So if I want to make an action out of peel dice, I don't need to do something like that. So I have no parameters, and I call peel and dice method, like this. So I just did one task out of my method. And because I call directly start new, this task would be started directly. I don't need to go on later on and say, you know what, started and started and started. Now, because I had a dependency, I said fry onion, it's dependent on peel and dice onions, I will need to make sure that, let me do like that, I will need to make sure that fry onion is called only when peel and dice it's done. So what I will do here, I will use some, ready-made ingredients in my kitchen, and I will just put them, I will show them to you instead of staying for hours here and me writing code. I'm just using, ready-made stuff. And I have fried onions, which is dependent on the peel and dice onions. And I say that peel and dice continue with. So what I say actually is that as soon as you are done with peeling and dicing, just continue with this fried onion. It doesn't matter when. It could be right away. It could be later. I don't say when. I just say after this time. Then I can do the same for the second step. So I can do dice the meat and add some spice and cut and clean the chilies. All those stuff actually are completely independent of each other. So I can do that by just adding, just creating 3 more tasks. So I'll say, okay, I will have a dice the meat task, which will be started after you call dice the meat. I will have add some spice. I'll have cut and clean the chili. So every single one of those tasks are now started in parallel. Of course, the only constraint I have here is that I have enough horsepower. So I have enough people in the kitchen, for instance, to do that. A task wouldn't start to run as long as I don't have a processor ready for that work. And next one, it's the first cooking. And if you remember, we had a dependency that the first cooking could not be started before all other steps are done. So let's try do that. Task. First cooking. cooking equals task dot factory, and factory like that. And now the factory class has a method called continue when all. And the name is quite self-explanatory. It says when all of those tasks are done, you should continue with or create a new task and run it. So it's some kind of barrier that I'm creating in my application, and I'm saying, let's all meet there, and when we are done, we will continue with some new work. So I will do continue when all, and in continue when all, the first parameter is a task array. So I will create this task array, new task array, and in that array I will have the first one, it's add water. That was the first, the last step actually of the first step. Then I will have dice the meat, like that, dice the meat. Then I will have add some spices, and then I will have cut and clean the chilies, like that. So this is my array of tasks that I need to make sure that all of them are done before I continue with my application. And the next parameter is an action that takes a task array, and it's called a continuation action. The task array is actually all those tasks that I have previously added to my list. So let's do that. And I don't need this parameter, so I'll just ignore it. I call it underscore. And then I go and say, you know what, whenever you are done with that, just run the first cooking. Let's go to the next step, and I have peel and dice and then second cooking. I can actually, be a good cook and just take this step 3, which is ready-made, peel and cut the potatoes, and then I have second cooking, and then same thing for the fourth step. Like this, and then I do the step 4 thing. Cut the peppers, and then final step. Is there something more that I need to do? Yeah, I need to wait. I need to make sure that the final step is done, because otherwise I will just say start, and then I'm taking the timing, and then it's 0. Because I never got any chance to do anything. I just start everything, and I'm never waiting for the end result. So let's do a final step. And if you would have used a thread, for instance, it's called join, but if you use a task, it's called wait. So I'm saying, let's wait for that to be done. Now we have a parallel version, or more or less a parallel version of our application. Yes, sir? So I use underscore because this method, or this continue and all, takes one parameter, which is a task array. So this is my task array. I could call it X, but the problem is that I don't use it inside the method or inside this call. So I would rather call it like that, and I will show the people that's an ignored parameter in my method. Here I have empty. I have no parameters into that action, so it's an action without parameters. And the only way to show that you don't take any parameters is with empty braces. Okay. And for that you got the book from me. So if you ask questions, you might get some books. I have some of them. Come after that for that. So let's run the application now and see what happens. Now it feels like I'm still. Oh no, yeah, that's right. So now I'm doing some of the tasks in parallel, and I already gained like 45 minutes by just doing parallelization on my tasks. No data parallelization whatsoever, no divide and conquer whatsoever. So where can I use divide and conquer? The biggest, let's do that again. The biggest time consumer in my application right now actually is there are two of them. The first one, it's dicing the meat for 8,000 seconds. Then I have the cooking. I can't do anything, in speeding up the cooking process. That's something that I always need to wait. That's something that will always represent my sequential part of my application. So no matter how many will be in the kitchen, we'll still have to cook it for 40 minutes. We'll still have to cook it for another 10 minutes. We'll still have to cook it for another 5 minutes. So those are some invariants in my problem that I won't be able to change. So I need to do some more. So if I look at how it's implemented now, actually the dice the meat method. So let's go and find it. dice the meat, I just say for every single piece of meat or for every single gram that you have, you need to chop it by hand. And that will be like 20 seconds per piece. You have 400 pieces, you'll get 8,000 times. But that's a bit, you know, that's a bit, let's say, stupid, if not nothing else. So what I need to do here actually is just to just create a method. Let's call it dice the meat. So it's private void dice the meat, like that. Parallel, so we know what we are doing here, parallel, like that. And then I will do something else. I need to do it, you know, in some kind of divide and conquer way. Divide and conquer means that I could look actually at the whole meat. I will start it in 2 pieces, and then because I have 2 pieces, 2 persons or 2 of my processor will start now to divide in 2, and then another 2, and then as soon as someone is available, we'll start to dice to do that thing. So I will do cut the meat in half. Cut the meat in half, like that. And I will use 0 as a starting point, and end point is ingredients dot meat dot length. So I know exactly how long do I need or how much do I need to go. And one thing I have in here actually, what I had before was 2 calls to the cut in half for the left side, cut in half for the right side. But in .NET 4, together with TPL, another class was introduced called the parallel class. And parallel class has some methods. One of them is called parallel.invoke. And parallel.invoke takes a list of methods or a list of actions actually. So what I'm sending here, I'm sending some actions, and I'm saying to my algorithm that, you know what, those 2 are completely independent of each other. Whenever you find the resources or whenever you find the time, you could actually do those in parallel. The nice thing about that is that the overhead is so little, so even if I'm running that on one processor machine, it still doesn't add so much to my performance. So I can show you at the end of this presentation that if I change everything and I say I have only one processor, we will not get so much overhead compared with what we had before. So we'll still be around, you know, the 200 minutes limit that we were before. So let's start this application again, but in order for us to have something working, we need to change this dice the meat with dice the meat in parallel. Where was it? Here. Yeah. Yes.
Why didn't you use continue with dot continue with dot continue every time while you're creating a task? Is there any reason?
There is no specific reason, but actually I think parallel.invoke shows better that this is a divide and conquer of the problem. If I say continue with dot, continue with dot, continue with dot, that's the question. Why haven't I said continue with dot and I created new task? Because if I say continue with, then I will have to wait for the previous one to be done in order for me to continue with another task. So the only thing would be that I will just create everything like I had before, and instead of having method calls, I'll have tasks created and waiting for each other. So it will not be parallelized at all. Okay. Come and see me, and I can I can assist you with that. Okay, so I will just change the dice the meat to dice the meat in parallel. I will compile the application. Everything looks fine. Let's try to run it. And now let's look at the machine how we load the processor. Now we are cooking the pot, and because of that we need to wait. And that I call a big improvement. We got down to 109 minutes from 200 minutes or 199 minutes that we had before. What do you think? Okay, but you know, like a used car salesman, wait, there is more. So let's see what we have more here. We have some result parallelism. In a result parallelism, all our algorithms actually are defined in some data structures and how you can decompose those data structures in order to solve a specific problem. So what we have a geometric decomposition, meaning that I could decompose data in such a way, if you have a matrix, you will do every line, or 2 lines at a time, or whatever. If you have a cube, you might do a matrix at a time. So you have a geometric decomposition of your data so that you could run in parallel. If you have some recursive data, you could actually do the recursive data. You could just take data and then, recursively split it into half and do some more and split it into half. A classic example would be a quick sort, for instance. In a quick sort, you just find, somewhere a pivot, and then everything on the left would be sorted in parallel with everything on the right, and then you can do that double recursion as long as you want, and then you will get at the end you'll get a sorted list. And then you have some data parallelism when you can apply same method to different. You can send data to same data or different kind of data to multiple processors that will be run in parallel. So you get this data parallelism in your application. So let's try to look at some more demonstrations here and see how can we do this data parallelism. One thing that was not yet addressed, actually, it's how we do with peeling and dicing. Let's think about it. I have like 10 or 20 or whatever number of onions and whatever number of potatoes, and the way I'm doing it here is that everything is considered a big chunk of work. So it's called peel and dice, and everything would be done in a single chunk of work. So let's do some changes to this one and create a new method called peel and dice parallel. And then with this one, I will actually do a for each. That's the first step, because I can see that what I have in here, it's the same kind of work over and over again. So I will say something like, for each var ingredient in ingredients, like this. What I do here is doing a peel of the ingredient, and then peel actually returns an ingredient back, so I could use the result, var result. This would be, my already peeled onion or potato, and this I will send on to the dice method, and dice takes again one ingredient, so it's the result that I'm sending in as a parameter. And you will see in a minute why I choose this kind of version instead of doing, method call into a method call. So let's do that. But it's still not parallel. So what do I use then? I use parallel.forEach. So parallel class has 3 methods that are interesting: parallel, parallel.for, parallel.forEach, and parallel.invoke. I will use parallel.forEach, and for each actually takes as first parameter the array, or the list of data, and then a second parameter will take a list of action that will take as a parameter this t source data. So I will use ingredient. I can call it whatever I like, but I will call it ingredient just to follow the same kind of pattern like we did before. And this one will go into this action that I'm creating here. So this one now is a lambda expression that uses an ingredient as a parameter, and it does exactly what my for each did before. And by doing that, I just parallelized my parallel.forEach, my for each loop. So let's try run it again. Now, because we have so little potatoes and it takes like 1 minute each, we won't see such a big improvement in that. But it's still an improvement. It's still a better usage of our resources than we had before, because I will not have someone now waiting for peeling or waiting for the dicing. Yes, sir? Sorry? No, I'm not. You're right, actually. Yeah, you got the book. Yeah, you are completely right. I never called that method. So let's look for peel and dice. Yes, yeah, you were right. So that's why we didn't get any improvements, yeah? So like this. And like this, yes. Thank you, sir. So let's do that again. Now I'm calling the method, but we are still getting, once again, we are not getting so much performance. Yeah, it took even longer, but it's not the case. I think I have a big virus in my machine. No names, no point, no, yeah. 99 seconds. Woohoo! Under 100, so that's good. I beat Windows. So that was actually, that was one way to do data parallelism. I just want to point out something. I showed that to someone, and then the next thing he does at work next day, he goes to his application and said, you know what, I had a parallel, I had a for each loop that it took, you know, like forever to do. Now I'm doing a parallel for each, and it will solve all my problems. What he forgot actually was that he was doing some kind of ASP.NET applications, and in every iteration he was using the context, and because of that you can't do the parallelization as he expected. So just because I showed it here, it doesn't mean that it will work in your case. You need to be sure what are the dependencies between different steps. So in my case it works exactly because I know that the dependencies between different steps are so small. Or are inexistent actually, so I can just do the stuff. I can take every potato, you know, by itself and treat it, or doing whatever I have to do with it. And we have a specialist parallelism. A specialist parallelism when you have a fixed set of data or a fixed set of tasks that your data will go through. And we have two specific cases here. One is called a pipeline. So in a pipeline situation, you get one thing, you know, that it does something, it returns a result, and the result would be sent to another method, and then the result to another method. The first method actually, or the second method, will be always dependent on the result from the first method. But if you do that several times, actually you could do something like that in parallel. So let's suppose that I take, you know, I take my wife to help me peeling and dicing the onions. Of course that she will do the dicing, I'll do the peeling, you know, I don't want to cry in the kitchen. So I will do the, you know, the sharing of the work in the kitchen. So I will start peeling. She cannot start dicing as long as I'm not ready, I'm not done with my peeling. But as soon as I'm done with the first onion, she can take it and dice it. And then when I'm done with the second, she can take it and dice it. So she would wait on the first iteration, but then we will work together on every second or every other iteration until the end. After I did the last onion, you know, I can be man enough, and now I can chop it myself because I have nothing else to do, and she might not be ready with the previous one, or, you know, with the crying before. But I will have two different you know, lines or pipelines of work. Or you have an event-based coordination. Normally, all the events that are created in .NET Framework are supposed to be asynchronous, but the implementations that we got, it's actually a synchronous one. What does it mean? It means that every time you subscribe to an event for one of your objects, the methods will be called exactly on the order that you actually subscribed. So if you have a button click, for instance, in your window, and you get 3 methods, the first method will be called the first one that you were just added to the list of the delegates of your event, which is wrong in my personal opinion. The reason I consider that wrong is because you shouldn't be dependent on the order of the methods that they are called. So they should be able to be called all at once. But quite often the implementation we do, it's based on this order. So it might not help anything every time that we are expecting, and Microsoft found that is not really the case, or it is not really the best way to do it, you know, just making everything asynchronous and run it that way. But if you think from the beginning in your application as an asynchronous application, and the way that you do all those events handling, then you might actually get some performance boosting in your application. So let me show you how I did the pipeline. And let me go back to this machine. So the pipelining is actually exactly what I said before, the peeling and dicing. And what I can see here is that I have a method called peel, and then I would like to continue with dice. And instead of doing that like I'm doing it now, I will do it with help of some tasks. So in order for me to create a task out of the peel method, I will need to create a task of ingredient. The task of ingredient, actually, which is called, let's call it peel, equals task.factory.startNew ingredient. So I'm sending I'm returning some ingredient data from ingredient like that. I'm returning an ingredient from my method, and what I'm sending in, it's my function, and the function would be no parameter returns peel ingredient. So I need a func that will return an ingredient, and pill is nothing else than that. So this is my pill method. Now, pill will do something like pill dot continue with, and then continue with will take as a parameter this task of ingredient, meaning the previous method. So I will take just t goes into dice, but now I have no result. The result is actually part of t, so I have t dot result. Like that, close the parenthesis, and we are done. Normally we are done. We are not really done. So let me show you something. Let's do a console write line, start peeling. Peeling. Or yeah, whatever, and done with that. Control V. Done. So if I'm starting that, let me see if I can manage doing this. We got start peeling, done peeling, start peeling, done peeling. So it's very fast. I never get a chance actually to do everything the way it should. Or no, I think it's wrong that way. Yeah, I need to move that outside my for each just to show what I needed to show. Outside parallel for each, let's do like that. And like that. And like that. So I got start peeling, done peeling, and that's all. I mean, I never got any chance to see, okay, I start doing the onion, I start doing the potatoes, or whatever, because everything was done pretty fast. Why is that? Sorry? I didn't wait for my tasks to be done in the parallel for each loop. So I have a problem there because I need to do that a bit different. What I need to do actually is to say to this second task like this. I have a parameter called continuation options, task continuation options actually. Task continuation options. And it's called attach to parent. If I use the attach to parent, I will say, you know what? Parallel for each will never be done as long as you have something to do. What I did before is just creating and starting a lot of tasks by never waiting for them. By doing an attach to parent, I will say, okay, the parallel for each now has to wait for them in order to report outside that I'm done with the parallel for each stuff. If you just use parallel for each, it's smart enough to wait for all the work inside, so you don't have to deal with waiting and combining those kind of stuff. So let's start that again, and let's see if we can get, yeah. Let's see what we got here. Yeah, and it's a lot of data here, and I don't get to see it. Let's try again. F5 and pause. So we got twice start peeling, but now we get peel the onion, peel the potato, dice the potato, dice the onion, and so on, and so on, and so on. And we will do that for as long as we have the onions and potatoes to do something with them. I'll just not run that because I did a pause and then the timing is not right. So now let's see exactly what happens. 93 minutes. So we still gain like 6 more minutes by doing that pipelining. Okay? So let's go back to my presentation. If we look at our supporting structures and implementation mechanism, we got some, the result will be that we have some code. What the whole presentation actually were some of the supporting structures and implementation mechanisms existing. What Microsoft did in TPL and what will come in the next version of the .NET framework, actually, they were using those kind of patterns and they implemented it in their applications. So you have a lot of program structures, for instance. Task class is one of those. You have the parallel class that is used for that. You have data structures. You have a system.collections.concurrent now, so you have a lot of concurrent collections that you could use from there. You don't need to implement them on yourself. Units of execution management. If we look at different ways of doing that. For instance, in a Unix environment, you will have process, you'll work with processes. In a Windows environment, you will work with threads, for instance. That's what we are actually running on a processor. The tasks are a way for us to just create those units of executions and making a final grain division on those. Some communication mechanisms, mailboxes, MPIs, and stuff like that. How can you communicate between different tasks, for instance, so you get all this kind of functionality? And synchronization. Synchronization is very important because you have the sharing of state. Well, as I said at the beginning of this presentation, we really need to make sure that that when we have the sharing of state, we do the right thing. So first thing, it's first. If you have to share, don't. You know, the best way to share data is not to do it, because if you don't share the data, then you don't have any problem. But the reality is a bit different. Normally, if you use languages like what's called Erlang, for instance, they have no sharing of data. All the data is immutable over there, so you need to deal with that. So by not sharing, by just sending the data, you know, as an immutable data, you don't have a problem. If you need to share data, try to share it as a read-only data. So if I give it to you, I don't care about whatever you do with the data. You can do whatever, but don't expect me to take back whatever you did. I can do that, but it will not be guaranteed. Data isolation. So if we can create smaller domains in our application, for instance, say, you know what? All this module will actually share the data, but outside we have no sharing data. We have only read-only data that we are sending back and forth, or we don't share at all. Then you have a better control of the data. If you start putting locks on, on your objects outside of your domain, then you might create problem, or you might open for problem that some other might create in your application. And the last part is synchronization. Synchronization, it's hard. I mean, that's the thing. I mean, it's not hard to implement it. It's hard to think about it. It's hard to follow whatever it happens. There are different ways of doing synchronization. For instance, at the processor level, they work with something called memory synchronization, or FANCIs. The processor might choose to rearrange your data, but when you have something like writing, they will make sure that the writing is actually done in the right order, not before reading or after reading, so those will not be changed. But if you just read data and they can see that there is no dependency between those, then you have no problem. You have some barriers. For instance, continue when all, it's this kind of barrier. We are waiting for all our first 4 steps, for instance, to be done in order for me to continue. So it's a very nice way to go with that. And the most used synchronization mechanism in our application is mutual exclusion. And the problem with mutual exclusion is that actually it's the one that creates can create big problems in our application. That's namely the deadlock. Yes. So deadlocks, in order for you to get deadlocks, it's not enough to have mutual exclusion. You have to do 3 more mistakes. Let me put it that way. Or you need to do all those 4 you need to have all those 4 conditions at the same time. So the first one is mutual exclusion, meaning that if I get access to a resource, nobody else can do that. But if I do that and nothing more, for instance, I'm not doing and holding and then waiting for another resource to be freed, then I have no problem. I won't get any deadlocks in my application. But if I need to get a lock on the other resource, so I get the first one and now I'm waiting for the second one to be done, I will be 1 step closer to a deadlock. The second one, it's no preemption. What does it mean? It means that I can wait there for as long as I want. And nobody can come to me and tell me, you know what, now it's done, you are done waiting. And because of that, I will have, I will be, again, 1 step closer to this one. And the first or the final step would be to have a circular wait. So let's suppose that the first task is waiting on resource 1, and then, or it got a lock on the resource 1, and then it's waiting on the resource 2. The second task got already the lock on the resource 2, and now it realizes that it needs the resource 1. And both of them are waiting on each other, but no one is actually, wanting to let the other one do stuff. And because of that, you get the deadlock in your application. And the biggest challenge with deadlocks is actually they are pretty hard to spot. The good news is that Visual Studio 2010 has built-in support, built-in tools for that, so you can use actually, and you can get some indications what happened in your application. Because of the multi-core paradigm that we are actually witnessing, those kind of problems will become more and more actual in our application. More and more of the application outside there will have these kind of problems in them. Because we are not thinking about that. We tested on our application. I had two processors. I had no problem. It works on my PC, no problem whatsoever. But when I put it in that server that has 24 cores in it, and everything runs whatever order they want, I might get that deadlock. So that's one of the biggest challenges that we will have to face as well when we go into this one. So I have a nice picture. The whole presentation actually it should be available on ComNet. You might be able to download it. So you will have this. I put it some of the patterns that I talked about. How do they relate to each other, and how should you look, and what would be interesting for you to look out for actually in your application. And yeah, that was about it. We talked about some of the definitions. We looked at how to create a parallel application. We talked about finding concurrencies in our applications and strategies to exploit those. Some algorithm structures in our, how can we do those algorithms, how can we organize our application. Then we had some supporting structures, and we talked about sharing state and deadlocks, of course. We can't talk about sharing states without talking about deadlocks. We talk about how to make a goulash, and then as well how to get some help in the kitchen. That's, yeah, that's about it. There are some, thank you. There are some resources that I recommend. Patterns for Parallel Programming, that's actually, my presentation, it's a ripoff of that book. So whatever I'm talking about, it's better explained in the book. So I warmly recommend that book if you want to do that. It's like the Gang of Four if you look for design patterns. That's no other book yet on the market. You have a concurrent programming on Windows, and Microsoft has this one as well, parallel programming, both for C# or for .NET and for C++. So it is available at the stand. O'Reilly, if you want, I can give you some coupons for discount. I have to give some to some people that ask some questions here, and I still have some of them. I have an enterprise library, and I have a two C++ books. So if you ask interesting questions, you might get some of those books as well. Conclusions, final conclusions, let's say like that. I show you the hammer, I show you the nail, but don't use it on the bunny, please. So yeah, embrace parallelism, man. Thank you.